So as Wopke said, I'm going to talk about complexity. And what I mean by this is ecological complexity. And there's actually quite a bit of literature on complexity, and I've brought some books, but not here. Maybe I can share them later on this topic. And when preparing for the talk, I came up with this line of argument that when we bring together different crop partners in an intercropping system or in a strip cropping system or in a strip intercropping system, then obviously we're going to increase complexity by increasing the number of interactions. And whoever has of you has dealt with an intercropping system has already probably made this experience that dealing with intercrops can be dealing with lots and lots of different, sometimes surprising interactions. And that's captured nicely by the term complexity. And the subtitle, Hoping for the Best, I hope that later on you will understand what I mean by this. That's basically one of the different options to deal with this complexity, but not the only one, fortunately. So my talk is structured like this. I give you a very short introduction to what ecological complexity can be understood by. So what is complexity? Then I will show you some examples of how intercropping systems are going to increase complexity. So ecological complexity as a or increased complexity as a consequence of diversification, in this case intercropping. And I will show you two examples, two case studies. One is more about the agronomic aspects, and the other one more about pest control. And you'll see that I will demonstrate, and possibly that rings with you as well, with your own experimental experience, that there's, let's say, strange things going on. And we could call them complex. And then in the last chapter of this talk, I'd like to explore the different options of how to deal with this increased complexity. And as I said, one would just be hope for the best. And maybe already now, I'd like to bring in this word or this term, this idea of compensation, which may help us to deal with this increased complexity. So what is complexity? What I did was to look into the ecological literature and have a look at the characteristics, not definitions of complexity, but characteristics of complexity. And if I ask you this question here, how do you notice complexity in your own experimental data? Maybe someone wants to volunteer. Yeah. Variability. Yeah.
Strong interactions.
Strong interactions. Yeah, I would think so too. Yes. Yes. Yeah. Absolutely. Anything else?
Non-linear.
Yes. Non-linearity. Very good. Yes.
Number of treatment factors.
Number of treatment factors. Absolutely. Yes. So number of supervisors. That makes a study very complex. Yes, I agree. So what I found in the literature, I grouped around 3 different themes: multiplicity, so different number of, or a higher number of elements. Yeah, so multiple elements, multiple dimensions, diversity, causal heterogeneity. All these terms are mentioned as characteristics of complexity in the ecological literature. There's also a theme of time. So time lags, for example, feedback loops, all this contributes to complexity. And also some that have to do with processes. So the theme of processes is also outlined here with various characteristics of complexity. Nonlinearity has already been mentioned. There are a few others, and I'm not going into detail of them, but usually what we're looking at when we're doing an experiment is just these two. We've got more elements and more interactions, maybe. Yeah, but this slide is really just to show you that there's more hidden complexity. Yeah. Okay. So and this is this Asian Go game. I'm not sure. Has anyone played this? Yeah. Yeah. You. So it's a bit like chess, but in a way. Hmm? It's a war game, yes, but it's also it contains very simple rules, a set of very simple rules, and gets very, very complex, even more complex than chess. Yeah, so that the supercomputers a few years ago weren't able to beat trained people at Go, but at chess. Yeah, so that's the complexity that you can see there, but with very simple rules. So from very simple rules, you can just by iteration and by interaction, you can get very high degrees of complexity. And this is also the idea behind, or the finding behind Robert May's famous paper on chaos in the 1970s, when he worked on population, on the equations encapsulating population buildup, and by just reiterating the same, the output into the input, you could show that what's generated by this very, very simple rule is chaos, unpredictability. So we need to be careful as ecologists, because not everything might be as it is. And when we try to predict something, it's sometimes very, very, very difficult. Okay, I show you two case studies in which increased diversity or intercropping has increased complexity. And what I refer to first in the first study is only, first of all, the statistical complexity in the number of interactions that are going on, because that's relatively simple to understand. But generally, as a problem with diversification, as intercropping, this leads to higher ecological complexity because there are more elements interacting with each other. And why is this a problem? Why is complexity in this case a problem? Because we've got lower predictability. Because so if there's an unknown interaction happening, then it's difficult to predict how the whole system will behave. So there's also lower transferability from one environment to the next. Let's say lack of generalizability from one to the next. It's high context dependence or high conditionality. Basically, all these three terms express similar ideas. And maybe paradoxically, you have wondered already, and we've talked about stability this morning already with Luke. Diversification is known to lead to higher stability, but at the same time, if diversity also makes systems more complex, then that might actually destroy this increased predictability. So I've tried to highlight this in this very simple graph. So at the moment, there might just be, this might just raise questions. And I'll come back to this at the end of the talk. So let's start with the first case study. And it was a monster trial. It was a 5-factorial intercropping trial. And most of you who are doing experimental work in the field will have one factor that is intercropping. So the monocultures and the intercrop. And you will probably combine that with any other number of factors, but perhaps not with 4 other factors. I'm not sure. That's quite mad to do that. I'm not sure who came up with this idea.
Maybe Benedict?
No.
I just said he would have needed it.
I think you did.
Okay.
No, I'm not that mad.
Yeah. So usually I would guess from the literature and also looking at your posters that typical experiments would show 2 factors, 3 factors, yeah, maybe plus another one. So in this case, we had apart from the mixture with 3 levels of the monocultures, 2 monocultures of fava bean and spring wheat, and the substitutive mixture, we also had 2 different densities and different fava bean genotypes, 2 different fava beans, and 12 different genotypes of the wheat. So everything combined with everything, and that resulted in 67 treatments. We added a few more monoculture plots because they're really critical for the analysis. So that in the end, we ended up with 320 plots per site. So these are 4 factors, and the last one is the environment. So we replicated this over 2 years at 2 sites, but not with all the combinations, because one of the sites there the experiment failed, or it just went another way, let's say. Okay, so that's how it looked like at the beginning, at the establishment at the 2 sites, and there are a few data on the methods with. Oops, I'm sorry. No, I need to go back like this. Yeah. Okay. Okay, there we are again. Right. So row distance of 21 centimeters, relatively small plot size of 10 by 1.5 meters. So as I said, 2 sites and a total of 2 years with 3 environments. So I'm not going to show you a lot of results from this because it's obviously generated lots of interesting results, but just as a taster for the whole thing, yeah, lots and lots of different interactions of these different study factors. Yeah, so environment having a very strong effect, like in basically every field experiment you are doing. But the real point here is that we've got a high number of interacting factors, yeah, and even though the three order well interactions, thank you, are not significant in this case. Yeah, 6 of the 2-way interactions are significant, which makes it really very difficult to explain the results and to find some generalizability. So this is just the net effect of the comparison between the monoculture and or the monocultures, the 2 and the intercrop. And of course, there are other ways of expressing this. This is, for example, the land equivalent ratio, and there the complexity does seem to be a bit reduced in terms of having not so many interacting factors being significant. But generally, we've got a relatively high degree of complexity, and you could just say, okay, the consequence is that I'm never going to do any more 5 factorial experiments anymore. I just don't want to see. Yeah. So then, but they're still there. I mean, if we look, then they're there. Yeah. And they don't go away by not looking. Yeah. So that's perhaps not an option. But usually we don't have the resources to do a 5 factorial experiment. Yeah. So we were very happy and very fortunate that we were able to do that. But it brings up a complexity that really makes it very difficult to think about what is transferable. Yeah. If I did a 2 factorial experiment instead and just thought, yeah, okay, we can do this in another environment or with a different management. No, we can't. The effects are different. Yeah, so that kind of complexity makes management recommendations very difficult. Okay, so the next case study is also combining different factors, but here, and I'm also going to show you some effects, let's say complexity in terms of statistical interactions. But here, the main focus is more on the interacting processes. Yeah, so it's ecological pest control, and the idea here was that if we combine different diversification measures, in this case intercropping and flower strips, can we then basically improve pest control overall? Is there an interaction going on between intercropping and flower strips, and what happens to the pests? Yeah, basically in this case we chose aphids in cereals and in non-cereal other crops, in this case fava bean and red sea poppy. And then in addition, we also looked at the weeds, what was an organic management without herbicide use. So in this case, we just asked, what is the role of weeds in this pest control? The experimental design was a very large experiment because the plots needed to be very, very large. The reason is that here we've got the flower strips that are, I don't know, 6 meters by 24 meters wide. And then we've got a control strip here, another flower strip, wildflower strip here, control strip there, and then flip-sided on the other side. You can see that's the reverse order. Yeah? So it's not, let's say, it's 4 replicates there with 4 blocks. And then within each of the flower strip treatments, we've got different diversification, crop diversification treatments. In this case, we had two monocultures, one intercrop. It was a non-substitutive intercrop, so more following, let's say, farmer practice in this case with a slightly higher density. And then we've got a living mulch treatment that I will here not include in the analysis or in the discussion because in our way it just didn't work. Yeah, so we just have a simple intercropping system combined with the wildflower strips. And then you can also see that we did different at different distances from the wildflower strips. We sampled the aphids and their predators as well, also the weeds, because it was known from the literature that the farther move away from the wildflower strip, the lower the effect of the predators or the natural enemies on the pests. So we wanted to see that if that's the case. Also, that was the reason why we made these plots so large. So at least that we had, I think, 24 meters wide there, or 25. Okay, so over time, so this is that was the spatial overview. This is the overview over time. So first, as I said, we had a combination of fava bean and wheat, spring wheat and spring fava bean, spring sown fava bean, plus the monocultures. Then after that, there was a cover crop, in this case field mustard, and followed by barley and poppy. So on the intercropping plots, we had intercropping. On the monoculture plots, we had monocultures. Yeah. And then followed by rye. I'm not going to talk about the rye, but basically I'm concentrating on these 2 intercrops and the effects. Okay, and you can also see some pictures of the flower strip. Was just to show very simply that flowers were there. Yeah. Okay, we also did, of course, record all the flowering occurrence in the flower strips, but sometimes you can see in practice or in science that flower strips don't really do what they are supposed to do. In this case, we were quite confident that they were providing floral resources. Okay, what did we measure? Beyond aphid colonization and predators, we also looked at weed biomass, at the coverage of the flowering, and also importantly at the insect-weed interactions, because we were interested in the basically how the weeds would in the middle of the field would be a resource for the predators, for the aphids. for example, for these hoverflies. I think I didn't bring any results of the grain yield here, but as I said, I'm concentrating on the story of the pest. Yeah. So what we saw, and this is nothing really new, is that in the intercrop we had a reduced colonization rate of aphids. So in comparison with the soil cropping bean, we had a reduced and reduced aphid colonization rate in the intercrop. That's mainly because we've just reduced the density. Yeah. Similarly, we could observe as a similar trend here in the poppy, yeah. So that's basically what we would expect here because of density effects.
So this is aphids per square meter then?
This is aphids. No, this is no, this is not the number of aphids. This is the percentage. The percentage or the proportion of aphid colonized plants. Yeah.
But that would not be affected by the vet.
It wouldn't, but it is, and the reason is.
Well, yeah, but that's a finding.
That's a finding.
Yeah.
And the reason is probably that the colonization itself, the host in terms of host finding, is disturbed by, or let's say, in a way affected by the presence of the other partner.
Yeah.
Okay. And also what we found was that there was a lower aphid colonization rate in the plots next to the flower strips. So we would expect that there was some predation going on. Yeah. So that's but only in 1 year. And I show you this table. It's an ANOVA table, or let's say a table of the GLM, the statistical model that lies behind it. And again, you can see a nasty three-way interaction there. Yeah. So what do you do with this? Yeah. So it's significant. You cannot just remove it from the model. Yeah. So it remains conditional. Yeah. On some special context. Yeah? So it's not easy to recommend that as the general effect of the whole thing to the farmer. And similar things go on in predation rate. I think someone here also had a similar reported a similar finding that if you have reduced pest incidence in the intercrop, then you also tend to find lower incidence of the predators. Yeah, they just go where the resources are. This is also dependent on the year, and again we find an effect in 1 year on the predation rate of the flower strip, a positive effect. Yeah? So that's nothing too surprising there, but my point here is more or less to show you all these, let's say, difficult interactions. Yeah. So Severin Hutt, who conducted this study, did a very good job in tidying up the let's say the models, yeah, and coming up with the minimal models here, but still in minimal statistical models, but still it's a remaining high complexity in there. And also the weeds played a role. We could see here that the soil cropping bean was as well as the soil cropping. Oops. Okay, so the soil cropping poppy and the bean were quite affected by weeds, and in comparison to that, I'm sorry, here the intercrop and also the barley itself and the wheat, so the cereals were not as infested as the other crops, as the bean and the poppy with weeds, and you can see then that the intercrop in itself helped to suppress the weeds. Also in the intercrop, we did a comparison with and without weeds. So that was hand weeded throughout the season, so that we should see, does the remaining weeds do the remaining weeds actually have a negative impact on the yield? That was not the case. So basically, also, we were interested, as I said, in the role of the weeds for the predator-prey relationships. And what we could see here was that the aphid colonization rate was negatively associated with some of the weed covers, so some of the flowers, so especially Matricaria recutita. Here, this flower here was giving nectar, giving floral resources to lots of hoverflies, which then in their larvae predate on the aphids. Okay, and finally here the flower strips. What you can see here in one distance, so close to the flower strip, you get a higher number of hoverflies here in the flower strip. Sorry, in the plot than in the control strip. Okay. So this kind of system with the aphids, the weeds, the hoverflies, or the crops, you can build it up like this. So the aphids feed on the host, and they are parasitized by parasitoids. Perhaps they are fed on by the predators. There's also inter-guild predation. So some of the predators predate on other or feed on other predators. There's also alternative prey that plays a role. There might be ants close to the flower strip, not in the field because they are not too disturbed, but then distance comes in again. And pathogens might also infect the aphids. So we've just looked at a few of these components. So the weeds also play their role. I haven't put this arrow here because it just would have destroyed the graph. But other than that, it's still there. So and you probably agree that this is only an excerpt of the real system. It's just one small element that we might be able to describe, but the whole system is much bigger. So how do you deal with such a complexity? And now I've shown you two examples, one from, let's say, more statistical point of view, lots of interactions going on, and one from a more process-oriented point of view. So how do we deal with this complexity in such intercropping systems? And so I would say there are two dimensions of dealing with complexity. You could either, first of all, you could try to reduce complexity, or you can increase it. So you could strive for low complexity and try to be in control of the system. So have high control over what is happening. So fewer elements. And a possible paradigm here would be current conventional pest management. Just very large fields, only a few crops, regulating pests with pesticides. You could also say, okay, I'm reducing complexity, but I don't really look. I don't want control. That would be quite stupid, I think. So it needs less understanding, but it's also very unambitious. So there's also less gain from complexity. For this, and many options of diversification would just be out. So we could move here to higher complexity, and I think we are already doing this by intercropping. Although, if I understand Maria correctly, actually we are coming from intercropping, and we are following a period of where someone forgot it. So,
reducing it all the time.
So maybe there's no other options than to increase complexity. If you are not striving for control, then there are no surprises. Yeah, it's just happening. Some farmers might actually act like this. Yeah, but very few. If they and really what we need is probably this high complexity, yes, but higher control. And then the question is it possible at all? Is it possible to, yeah? So where on this axis are we? Yeah. So that's, for me, that's an important question. And I can't give you the answer where we are or how we could come from here to there. But one key element there, I think, is compensation. Yeah. And so I've written here using compensation, and they're managing compensation to indicate that here, compensation is happening all the time. But here in this corner, we are striving to use compensation in a more informed way. Yeah. Okay. So how could that look like? So I've replicated the system with the aphids, this complex system, as a partially black box. We don't know what is going on there completely. Yeah, we will never be able to see everything that is in there, but at least we know a few elements there. But maybe we're not terribly interested, at least in the outcome, on all these different processes. Not on all of them, let's say. Yeah, but we are very much interested in the performance that is driven by this, at least partly. So the performance indicators is very important. And the idea is that compensation and resilience, I'm concentrating here on compensation. Compensation is helping helping us to deal with this complexity in the way that it reduces the number of or the variability that comes from this complex systems when we're looking at the performance indicator here. Yeah, so that's compensation makes the performance indicator like yield more stable. Yeah. So and before I show you an example of compensation, I'd like to give you the one possible definition. So compensation may be called a process by which a system is able to regain its normal state in response to losing a part of the structure. And in terms of intercropping, it's many times being cited as if, so coming down to this, if one component fails or experiences reduced growth, then the other component takes its place. So that's what in textbooks you find about compensation in intercropping systems. And maybe this kind of process, this compensation, is able to let us ignore some of the system's complexity. Yeah. So because of compensation, we can just say, okay, we may not necessarily be interested so much in every single process. We don't need to understand every single process in this partially black box. And this comes back then to the question of the paradox between how diversity led us to a higher predictability or lower predictability in this case. And I think this is already known, or has been known for quite a while. Diversity leads to low stability at the level of individual components, of course. Yeah. So this increasing diversity for the system makes all the different components even more variable. Yeah. But at this aggregate level, at the performance indicator, for example, at the yield, yeah, where lots of compensatory processes go in, their diversity leads to higher stability. Okay, I'm not sure about time.
It's okay. It's flexible.
Flexible. Okay.
As long as I allow you.
Okay. Okay. I'm not sure I've got a bribe on me. But okay. So just a few slides. Yeah. So this is about the question of compensation. And how can we understand it? And I've used it on this graph here. So basically, what we can say about compensation is that it's the flip side of competition. Yeah. So you're in this graph, I've plotted grain yield against relative plant density. Yeah. So number of plants here per square meter so not number of plants, but relative plant density. So this is the maximal plant density here. Is white on white. This makes it, yeah, so this. So 1 means maximal plant density. Yeah. So if you go from 0 to 1, you increase the grain yield. Yeah, that's very clear, but in a non-linear way. Yeah, so not proportional to the relative plant density. And these are monocultures. Yeah, these are monocultures. It's in every plant standard practice. Yeah, as you increase plant density, grain yield goes up, but in a non-linear way. But you can also flip it around and go from this side and say, okay, my maximum plant density was this, and now I lost 20% of the plants because of a pathogen or because someone ripped it out. Yeah. So we are here, and we are not losing proportional. Yeah, we're not losing 20% of the yield, but we are losing less. Yeah, because the rest of the plants, the remaining plants that are still there, they are producing more. They're using the remaining resources in a way. Yeah. So they compensate against this loss. Yeah. So this is a way in which compensation could be quantified. Yeah. As the difference basically between this curve here and this line. Yeah. So that would be a possibility to quantify compensation. And you can also do it for intercropping, of course. And then if you lose oats here, yeah, if you lose oats plants per square meter, then in the intercropping bean, not only the oats are going to compensate that loss, but also the beans. Yeah, they're going to increase their share until here at 0, there's no oats left, which is the bean monoculture. Yeah. Okay, so you can generalize this as a model of compensation, where you've got a contributor. So maybe I have this here, a contributor. So in this case, that would be plant density. In my example, that would be plant density. This contributes to the outcome, yeah, to the grain yield. Yeah. But then you also have a reductor, maybe a pathogen, yeah, that reduces this contributor. For example, seed mortality in one of the partners. But then you've got a compensator that leads to this behavior of this curve, which means that the grain mass per plant is increasing, yeah, as the number of. So if you multiply the plant density and the grain mass per plant, you end up with a grain yield. And you can also do this with lots of other ecological processes, for example, with pest regulation. Yeah. So pest control by multiple antagonists. You've got hoverflies, you've got carabids, you've got spiders and lacewings and so on. Yeah. And overall, you've got an antagonist abundance that reduces or does the pest control for the aphids. So you're interested in this outcome, in this pest reduction. But there's a reductor because some of these antagonist groups are lost, yeah, or some of the individuals. Yeah. What happens is that the remaining ones are going to create more, yeah, because there's less competition among these individuals. Yeah. So we would expect some kind of compensation there happening as well. Yeah. And as I said, competition and compensation really work in a flip side way. Okay. So that leads me to my conclusions. So intercropping may have several benefits for the agroecosystems, as we are discussing here in this whole course, but at the cost of higher complexity. So that is, yeah. So ecological complexity is higher, and also that means if we want to recommend any particular management, then that comes at a difficulty because we're not sure whether this is really transferable from one situation to the next. So in intercropping, as I said, helps with its economic performance and the pest control, but increases system performance. Increases system complexity. Compensation might be a key process that helps us to stabilize these complex systems and enables us to ignore some of the complexity. Yeah, so that we don't need full control because we will never, my opinion, we'll never get full control. Yeah, we can strive to understand more, but there's a limit. And these complex systems probably cannot be controlled at the individual process level, at the component level so much, but at the aggregate level, the outcomes can be managed via building and compensation. And that again means diversity, yeah, because we need all these different groups of predators to do pest control. Yeah, if they are all responding to the same disturbance in the same way, then we're losing that kind of compensation. Okay, I think that was it. Thank you.